Look up at Orion's shoulder and imagine this. One night, a familiar red star swells into a beacon so bright you can see it in daylight. People step out of offices, cars pull to the side of the road, and strangers point at the same patch of sky. The star is Betelgeuse, and it has been restless. As of 2025, observers report it trending to the brighter end of its normal cycle again, with fresh arcs of gas traced around it, signs that the giant is still belching material into space. In July 2025, astronomers using the Gemini North Alopeci speckle imager reported a probable direct imaging detection of a very close companion to Betelgeuse, seen in 2024 data near greatest separation. The faint star sits only about 52 milliseconds from Betelgeuse, about 6 magnitudes dimmer, and is likely around 1.5 to 1.6 solar mass pre-main sequence star. Some coverage nicknamed it Siwarha, her bracelet. Follow-up is underway, and the next easiest window to resolve it again is around November 2027. What does this change? Not Earth safety, and not an any-minute-now explosion. A close companion can help explain Betelgeuse's overlapping 400-day and 6-year brightness rhythms, feeding those dust arcs we keep imaging, but it doesn't mean a supernova is imminent. If you want the latest on Betelgeuse and other cosmic weirdness, tap subscribe so you don't miss the next update. So what exactly is going on now, and what would it mean if this titan finally lets go? To answer that, we need to understand the character of the star, the drama of recent years, and the physics behind a supernova you could see with your own eyes. Betelgeuse sits roughly 600 light-years away, close in galactic terms, yet safely distant for us. It is a red supergiant, born with more than 15 times the mass of our Sun. If you could swap it into our solar system, its bloated surface would swallow Mercury, Venus, Earth, and likely reach past Mars. It glows with a deep ember hue because its surface is relatively cool for a star, just above 3500 Kelvin, but its sheer size makes it over 100,000 times more luminous than the Sun. This is a thermonuclear furnace spread across a volume so vast you could fit 1 billion suns inside. Unlike our middle-aged, even-tempered Sun, Betelgeuse is restless. Its outer layers are a rolling sea of convection, with cells as large as our entire solar system rising and falling like the top of a simmering pot. Those convective plumes can throw matter into space. When hot gas rises, cools, and condenses, it becomes dust that drifts across our line of sight and sometimes hides a large portion of the star's light. We watched that happen in real time in 2019 and 2020. Overnight, a star many people knew only as a dot in Orion became a headline. It dimmed to the faintest level in centuries, and for a few weeks the familiar outline of the hunter seemed broken. The world asked, "Is this the end?" It wasn't, but the story was still extraordinary. Imaging and spectroscopy showed that Betelgeuse had launched a colossal mass ejection. The gas cooled into dust, which passed between us and the star and blocked its light. When the dust dispersed, Betelgeuse brightened again. That single episode reshaped what astronomers thought they knew about red supergiants. These stars don't just shed matter as a gentle wind, they cough it out in sudden, asymmetric blasts. Each outburst adds to a clumpy halo around the star. Those clumps are not just background scenery, they are the terrain the eventual supernova shock will have to cross. Betelgeuse's age tells another part of the story. Our Sun is 4.5 billion years old and may last another 5 before it becomes a red giant. Betelgeuse is a cosmic teenager, 10 million years old or so, and it is already nearing the end. The difference is mass. The heavier a star is, the faster it burns its fuel. Inside Betelgeuse, fusion proceeds in layers like an onion. Hydrogen fused into helium long ago. Helium fuses into carbon. Carbon burns into oxygen. Oxygen into silicon. Silicon into iron. The sequence races faster at each step. Hydrogen burning can last millions of years. Helium gets hundreds of thousands. Carbon might get centuries. Oxygen gets years. Silicon gets days. Then the star hits iron, and iron is a dead end for fusion. It doesn't release energy when you fuse it. When iron dominates the core, gravity wins. The core collapses in less than a second. What happens next is both violent and elegant. Electrons and protons are crushed into neutrons, and a flood of neutrinos, ghost-like particles that hardly interact with matter, bursts outward. Those neutrinos will slip through the star, the interstellar medium, and even through Earth with ease. But our neutrino detectors deep underground and under the ice are ready. They will light up hours before the star's visible light changes. For astronomers, that early neutrino burst will be the alarm bell. When the shock wave created by the rebounding core finally breaks out of Betelgeuse's surface, it will radiate high-energy light and then an optical surge. In less than a day, the red shoulder of Orion will become a jewel that rivals Venus. How bright are we talking? Under clear blue skies, you could look up and see it in daylight. At night, it could cast faint shadows on snow or sand. The light curve would climb, peak, and then slowly decline over months. At first, the color would be hot and blue-white as the ejector rush outward at thousands of kilometers per second. Then it would redden and fade as the expanding debris cools and as the radioactive elements forged in the blast, nickel and cobalt, decay and power the afterglow. The show would be unforgettable, and it would be safe. A supernova would have to be much closer, tens of light years, to threaten Earth's ozone and biosphere. Betelgeuse is hundreds of light years away. We are far outside the danger zone. No gamma-ray burst threat either. Betelgeuse still wears its thick hydrogen envelope, and the tight alignment needed for a beam to sweep across Earth is a long shot for a star like this. The sky would change, but not our atmosphere. Part of what makes Betelgeuse so intriguing is that it keeps giving us puzzles between these quiet years and the eventual finale. One of the strangest is rotation. You would think a star that expands to enormous size slows to a crawl as angular momentum spreads out. Yet maps have hinted that Betelgeuse's surface might be turning faster than expected for a red supergiant. That result launched theories that the star once swallowed a smaller companion, a dramatic merger that spun it up like a figure skater pulling in their arms. The outer layers show nitrogen enrichment, which suggests deep mixing. A chaotic merger could stir the star and carry processed material from the interior to the surface. That idea has staying power, but new work also shows how deceptive a boiling photosphere can be. Giant convection cells can masquerade as rotation in some observations. The truth may be a little of both. Some residual spin from earlier days or from a past encounter, and a lot of turbulence creating the illusion of a faster turn. Then there is the rhythm of its brightness. Betelgeuse doesn't just vary randomly, it has overlapping beats. A shorter cycle a bit longer than a year, and a longer swing of around 6 years. Some researchers have suggested that a faint companion could help explain the pattern, adding a gravitational nudge to the star's already unstable atmosphere. Others argue that the long secondary period can emerge from pulsation and convection alone in a star with Betelgeuse's dimensions. Directly imaging any close companion is difficult. Betelgeuse's face is mottled, its atmosphere is extended, dust veils complicate the view, but improvements in interferometry, tying multiple telescopes together to work as a single far larger eye, keep pushing the limits. As instruments sharpen, the star's neighborhood is coming into focus. Whether the extra beat is a partner's tug or a natural mode of the giant's breathing, the lesson is the same. Betelgeuse is more like weather than clockwork. If this helped separate hype from reality, hit like to tell the algorithm you want more deep dive space stories. Let's return to 2019 and 2020 for a moment, because that chapter still shapes everything we think about what comes next. The Great Dimming wasn't just a flicker, it was a window into the way red supergiants lose mass. The amount of stuff hurled into space in that event was enormous. Several Earths worth of material. Imagine a planet's mass lofted off the surface of a star and cooled into dust in a matter of weeks. That dust didn't just block our view, it joined a messy halo that surrounds the star. The next outbursts add to it. Over centuries, the environment around Betelgeuse becomes a patchwork of arcs, knots, and shells. When the supernova shock eventually hits those clumps, it won't be a smooth ride. We might see secondary flares as the shock rams a dense knot, radio brightening as shock-accelerated electrons spiral in magnetic fields, and echoing arcs of light as photons scatter off distant sheets of dust and take longer paths to us. The supernova won't just be bright, it will be dramatic and asymmetric, a fireworks show shaped by centuries of the star's own storms. History tells us what a naked-eye supernova feels like from the ground. In 1054, astronomers in China and the Middle East recorded a guest star that shone in daylight for weeks. It left behind the Crab Nebula, still expanding today and powering a pulsar wind that glows across the spectrum. In 1572, Tycho Brahe mapped a new star in Cassiopeia, and in 1604, Johannes Kepler observed another in Ophiuchus. Those events challenged the ancient idea of an unchanging heaven and ushered in a more dynamic cosmos. A Betelgeuse supernova in our era would be different in one key way. We are ready. Neutrino detectors will sound the alarm. Space telescopes and ground arrays will swivel within minutes to capture the shock breakout. Radio observatories will trace the expanding shell. X-ray and gamma-ray instruments will dissect the high-energy physics near the core. Gravitational wave detectors will listen for the subtle ripples of a core in turmoil. We would study the death of a star in real time from the inside out. That is the science. But there is also the culture. Betelgeuse is not just a hot ball of plasma, it is a point in our stories. Ancient Egyptians aligned temples with Orion. Cultures across the world wove the red star into myths. In modern times, its name pops up in films and books. When it finally explodes, the reaction won't be limited to observatories. News anchors will announce updates by daylight. Families will step outside together at night. City dwellers who never see the Milky Way will notice a star blazing through light pollution. Students will learn that elements were born in such fires, that the calcium in our bones and the iron in our blood came from stars that died the way Betelgeuse will die. For a while, the sky will feel like a shared experience again. Now, back to the present. The 2025 observations show Betelgeuse pushing up toward the bright side of its usual cycle again. Interferometers resolve arcs of gas streaming off the surface. None of that proves a supernova is around the corner. Most models still put the explosion tens of thousands of years in the future, but there is an important caveat that astronomers bring up whenever the question comes. The light you see tonight left Betelgeuse 600 years ago. Anything that happened after that, more dimmings, new outbursts, even the final collapse, has already taken place where the star sits. We just haven't received the news yet. That uncertainty fuels the fascination. When people ask if Betelgeuse could go tonight, the careful answer is yes, in principle. It is unlikely, it is not predicted. But because of the lag of light across space, it is never impossible. Let's talk about the day the star dies, because that's the part most people want to see in their mind's eye. The first sign will not be visible light, it will be neutrinos. Detectors like Super Kamiokande in Japan, Ice Cube at the South Pole, and the new Dune experiment in the United States will register a sudden rise. That alert will ripple across the astronomy community within minutes. Telescopes will tune to ultraviolet and X-rays to catch the shock breakout as it punches through the star's surface. For a bloated red supergiant like Betelgeuse, that flash could last hours rather than minutes. Then the visible light will rise. In a day, the red shoulder of Orion becomes a brilliant white-hot torch. Over the next week or two, it settles toward peak brightness. For months, it slowly fades. The ejecta plow outward, shaping a nebula that will be visible in telescopes for generations. Light echoes will add their own drama. Imagine a thin shell of dust far from the star. The first photons from the supernova blaze will rush past us in a straight line, but some photons will scatter off that dust and arrive later, delayed by their longer path. To us, it will look like arcs of light appearing in the sky years after the main event, as if the star were blinking through a fog. Radio telescopes will keep listening as the shock front accelerates particles. X-ray telescopes will watch as the shock lights up denser clumps. Every wavelength will have a role in telling the story of a star's death and the birth of its remnant. What will that remnant be? If the core collapse halts at nuclear densities and rebounds, it will leave behind a neutron star, a city-sized sphere of neutrons with the mass of the sun. It may spin fast and beam lighthouse-like pulses. If the star's mass and conditions push it further, the core could collapse to a black hole, swallowing light and leaving no heartbeat but memory and debris. Either way, Orion will be changed forever. Where there was once a steady red point, there will be a patch of nebulosity. Children will ask what happened to the hunter's shoulder, and we will tell them about a star that lived fast and died spectacularly. All of this makes Betelgeuse the perfect teacher while we wait. The Great Dimming revealed how quickly dust can form around a supergiant. Nitrogen enrichment hints at mixing, maybe stirred by a past merger. The rotation debate shows how easily our instruments can be fooled by boiling stellar surfaces. The overlapping rhythms of brightness tell us that pulsation, convection, and maybe companionship all shape how such a star breathes. Every outburst, every flare, every lull is data. The star's irregularity is not a nuisance, it is the experiment. We are learning how massive stars shed their outer layers, how they prepare the stage for their shockwave, and how their final moments forge the elements that make planets and people. Before we wrap, here is the core message again. Betelgeuse is a red supergiant about 600 light-years away. It is safe for Earth if it explodes. It has already taught us that massive stars lose mass in fits and bursts. It may have spun up from a past encounter or fooled our maps with surface weather. Its brightness cycles are real and complex. In 2025, it has again reached the bright end of its cycle and continues to blow off gas in arcs and plumes. None of this guarantees an imminent supernova. Most likely, the finale is still far away on human timescales. But because of the light travel delay, it is never completely off the table. That is why Orion still steals glances on winter nights. We are watching a star that might already have changed. If this brought Betelgeuse into focus and you want more clear, hype-free space breakdowns, subscribe, share this with a friend who loves the night sky, and let me know in the comments what you want me to cover next. One last thought before you go. One night, whether soon or long from now, Orion's shoulder will bloom with a light so brilliant the world cannot ignore it. For a few weeks, humanity will look up together. Newsrooms will cover the sky like a sporting event. Kids will drag their parents outside. Amateur astronomers will camp in parks. In that shared moment, we will see not just the end of a star, but the beginning of something else. The dust and gas that will settle, cool, and one day form new stars and worlds. Betelgeuse is restless, and that restlessness is telling us a story. We listen, we learn, we wait, and when the sky finally changes, we will be ready to watch it happen.